So to build off the idea of solving equations both graphically and algebraically, we can extend that to solving a system of equations. So a system of equations is a set of two or more equations, and the solution to the system is the ordered pair that solve every equation in that system. So for example, if I give you two equations and you graph them, where they intersect is the ordered pair that solves both of those equations. So let's start with example number 1. I've got 2x minus y equals 9 and x plus y equals 6. If I wanted to solve these by graphing, solve this system by graphing, first I would have to get them in y equals form, so I'd have to solve for y. So first one, 2x minus y equals 9. Start by subtracting 2x. Get negative y equals negative 2x plus 9. And then divide by negative 1 to get rid of the negative in front of the y. So I get y equals positive 2x minus 9. So when I graph that, I'm going to start at negative 9, and I'm going to go up 2 over 1. For the second equation, x plus y equals 6. To get y by itself, I just have to subtract x on both sides and get y equals negative x plus 6. So that tells me I have a y-intercept at 6 and a slope of negative 1. So down 1, right 1. So I see that these two lines intersect. Oh my goodness. I see that these two lines intersect at one point. The point here is 5, 1. So the solution to this system is the ordered pair 5, 1. I'll be honest though, solving for y and then graphing and finding a point of intersection is kind of tedious and it takes a lot of time. So instead, we can solve this system algebraically. When we do that, you probably learned this in Algebra 1, we can combine these two equations. Notice how the equations are lined up. The x's are together, the y's are together, and then the number on the other side is together. When I combine these equations or add the like terms from equation to equation, 2x plus 1x is 3x, and then negative y plus y, the y's go away, equals 9 plus 6 is 15. Now I have one equation that I can solve for x. If I divide both sides by 3, I get x equals 5, which, notice, is what we got when we actually graphed it. To get the y value for this, I just have to plug this x value into either of my original equations. I'm going to pick the second equation because there's less stuff happening here. X plus y equals 6. Well, I know my x is 5, so 5 plus y equals 6. Subtract 5. That means that y equals 1 again, which is what we got. So if I were you, I recommend solving it algebraically. That took way less time than actually solving for y and graphing. So for the next one, luckily on this one, it is already in y equals mx plus b form. This time I'm going to solve it algebraically first and then check to see if my solution works on a graph. I could combine them like I did here, but notice if I combine them, y and y is going to give me 2y, 2x and 4x is going to give me 6x, negative 3 plus 9 is going to give me positive 6. None of the variables went away, so it didn't actually make my life any easier. What I can do though is substitute. Since I know that y equals 2x minus 3, I can take what y equals in this equation and substitute it for y in the second equation. So instead of y equals 4x plus 9, I can write 2x minus 3 equals 4x plus 9 and solve for x that way. So I can start maybe by subtracting 2x on both sides and get negative 3 equals 2x plus 9. Then I'll subtract 9 and get negative 12 equals 2x. Divide both sides by 2 and get negative 6 equals x. Now I can take this negative 6 equals x and plug it into either of my equations above. I'll use the top one this time. It does not matter though. Y equals 2 times negative 6 minus 3. If I do order of operations there, I know that 2 times negative 6 is negative 12. Minus 3 is negative 15. So the solution here is -6, -15. Go ahead and pause the video and try graphing both of those lines to see if you get an intersection at -6, -15. We'll try just a couple more. So for this one, similar to the first one, I have one equation that I'm going to set equal to the other. 2x minus 1 equals 1/2 x plus 6. If I solve for x here, I'll start by subtracting 1/2 x. 2 minus 1/2 is 1.5 x. I'll add 1. And then divide both sides by 1.5 to give me x equals 7 divided by 1.5 is 4.667. Then when I take that and plug it back in for y, if I do order of operations there, 2 times 4.667 is 9.333, minus 1 is 8.333. So this is an example of where it's probably better to just solve it algebraically, because if you were to solve it graphically, you would have to estimate where those decimal points were on your graph. And lastly, solving this system on your graphing calculator, it's very similar. We're going to use our graphing calculator again. We'll go to our y equals, clear out what's ever in there, and graph these two functions. So the first one is an absolute value, so I hit math, go over to number. Number 1 is absolute value, and we're going to type in x plus 1. Then I just hit my over arrow to get out and hit, oh my goodness, just deleted it all. Now I'll hit my over arrow and type in minus 3. And then in my second equation, x plus 2, I'll hit graph. Okay, and I notice I only have one point of intersection there. So second trace, select number 5 and move to the point of intersection. Enter, enter, enter. Since we are solving a system and we're not just solving an equation for x, I do actually want the ordered pair. So your solution to this system would be -3, -1.